We're going to look at the one solid we haven't yet looked at, and that is the sphere. Like a circle, spheres are constant curvature. There are no edges, there are no vertices, even though it appears we have vertices where these meet. This is one continuous, smooth, curved solid. It is basically one continuous face, even though a sphere has 0 faces, because faces must be made up of polygons. Polygons have no curvature. So a sphere is just one constantly curved solid. And it's equal curvature. It's not something like a football, which has curvature that changes. It is a perfectly formed object where the curvature is equal all the way around. It has a radius, which connects a point on the surface to the center. So if you imagine the Earth as being a sphere, any one point on the ground connected to the center of the Earth, that would be the Earth's radius. We could think of it as also being a circle that sort of pivots around about the center. So if you imagine this circle right here is going to sort of just start to turn, but this point stays constant, so that's going to be sort of like a pivot point. This circle, as it turns, will sweep out this entire inner space, and it will create the boundaries of that sphere. We're going to go a little different route and start with volume. Since we don't have calculus knowledge yet, most of us don't have calculus knowledge, the formulas are much more difficult to derive if we start with surface area. So we'll start with volume and make things a little simpler. Now again, we don't have calculus to use. The sphere formulas are very, very simple to come up with using calculus. But we don't have that, so we sort of have to take a different approach. I'm going to start with this object right here. This is a cylinder, and inside of the cylinder is a hemisphere, half sphere. Also, this darker shape is a cone. So we're going to do this. We're going to determine the volume of this hemisphere by taking the volume of the cylinder minus the volume of the cone. That sounds a little convoluted, but the way this works is based on something called Cavalari's principle. Imagine a knife cutting through this object. Oops. We get what's called a cross section. So we take a knife, we cut this, we make a cut right here. Let me just make a cut. So let's say I just make a cut right here. So we slice this top piece off, and then we look down onto the piece we just cut. What we would see would look like kind of a washer. It would have this outer circle where the cylinder is, but then it would have an inner circle which would represent this piece of cone. So it's a little difficult to picture just by words, but that's kind of what's going on. And who says we make the cut there? We can make the cut here, we can make the cut there. That inner circle is going to change because the cone is getting wider as we go up. So that inner circle gets bigger. Here the inner circle gets smaller. The cylinder circle stays the same. The inner circle is going to change. Cavalieri's principle says, I can't get my, there we go. Cavalieri's principle says that all of these cross sections are going to be equal. And that's a little difficult to prove in this case, but I can explain it this way. Every piece of cone that we remove is being replaced by an equal amount of hemisphere. If all that is happening, then we can calculate the volume of this hemisphere based on this principle. Because all those cross sections are the same, that means the volume of the hemisphere and the cylinder with the cone cut out of it are going to be equal. So here's the volume of the cylinder. Pi r squared h, volume of the cone, 1/3 pi r squared h. Look at our cylinder though. The height is also the same as the radius. So what we end up with is pi r cubed, because this is also the radius, and we get 1/3 pi r cubed. And when we subtract those, we get 2/3 pi r cubed. That's the volume of a hemisphere, a half sphere. So to get the volume of a full sphere, we double this. The volume of a sphere, 4/3 pi r cubed. Believe it or not, that's the easy one. Surface area is much more difficult. But in order to do the surface area formula without using calculus, we need the volume in order to do surface area. It's kind of a little backwards notion, but that's what we have to do. So now that we have volume, 4/3 pi r cubed, we can move on to surface area of a sphere. One thing we notice is that a sphere has no base. All of the area is lateral. There is no base area. If I go back to the sphere, what we think is the base is this circle, and it's entirely inside. All of this area outside is lateral area. So we'll start with this figure. And let's just sort of not worry about this stuff just yet. Here I have a sphere. And what's happening here is there's this pyramid that's sort of drawn on the surface. Now again, we know that because the sphere has constant curvature, these are not perfectly straight. There's a little bit of a curve to them, but we'll work with that. So there's this somewhat square that's been drawn on the surface, and then all these vertices have been connected to the center, creating a pyramid. The only piece of the pyramid on the surface of the sphere is this base shape. And we've called the area of that shape capital A. We know that the height of the pyramid is equal to the radius because the distance from the surface to the center, surface to the center of that base shape to the center of the sphere, that's also the radius. So all of these are radii. The slant height's a radius, the vertical height's a radius, all of these are radii because they are all on the sphere. Here's a ratio of the pyramid's surface area to volume. Because the only piece of the surface that's outside is this, the pyramid surface area is A, capital A. All the rest of it is inside the sphere. The volume of a pyramid we know is 1/3 base area, which which is capital A, times the height of the pyramid, which we've already stated is also the radius of the sphere. So let's work with this a little bit. We can cancel the A's to get this ratio 1 over 1/3 R. We can clean that up a little bit. For the pyramid, the ratio of its surface area to volume is 3 to R. Now, I'm going to say, let's have N of these pyramids. So let's cover the entire outside of the sphere with this little shape. The smaller we make this shape, the less curved these sides are. The bigger we make them, the more curvature we need. The smaller we make these, the less curvature we have. So I want to make these really, really, really small, and I want to cover the entire sphere with them. Let's say there are N of those. It takes N of those little tiny pyramid bases to cover the whole sphere. That means the surface area of the sphere to the sphere's volume is the same as that pyramid ratio, which is the same as 3 over R. Because the surface area of the pyramid also covers the sphere, the surface of the sphere, those are equal. And all this volume, all those little shapes, volumes, the more and more and more of them I make, will eventually fill the inside of the sphere. So the smaller I make these, the more this gets to actually being equal. I should have made this approximately because, again, these cannot be straight. But if I make them really, 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 really small, infinitesimally small, really, really, really tiny, then the smaller I make them, the closer this gets to equal. Now we have something we can work with. We can set the surface area of a sphere over its volume equal to 3 over R. And this is why we needed the volume of a sphere first. Because now we can fill that in. We can cross multiply and get surface area times radius equals 4 pi r cubed. When we multiply this, that fraction goes away. We can divide both sides by r. Oops. And we get that the surface area of a sphere is 4 pi r squared. The simpler formula was actually the harder one to come up with. Technically, we're using calculus concepts here. There's a concept called a limit, where you make things really, really, really small, and you get them so small that they get really, really, really close to being zero. As we make these little shapes really, really, really tiny, we get their lengths to almost zero. We almost get an exact balance here. That's one of the first calculus concepts you learn, called the limit, where you make things really, really, really tiny, and you ask yourself, what is happening as this gets really, really, really small? And then you use that to do other things. Surface area of a sphere, 4 pi r squared. Volume of a sphere, 4 pi r cubed. Let's do a quick example. Here's a sphere, radius 12. Find its surface area, find its volume, both in terms of pi. Here's our surface area, 4 pi 12 squared. And this will give us 576 pi. Volume, 4/3 pi r cubed. 12 cubed. And then we multiply by 4/3. And there we have it. Surface area and volume of a sphere.